Question number 4. The fuel natural gas is mostly methane. Its combustion in oxygen is exothermic. CH4 reacts with oxygen and it gives CO2 and H2O. Explain why this reaction is exothermic in terms of bond breaking and bond making. This reaction is exothermic because the amount of energy which releases by making the bond in the product side is more than the energy that we need for breaking the bond of the reactants. Part B. Copy and complete this energy diagram for the reaction indicating the overall energy change, the energy needed to break bonds, the energy given out by the new bonds forming. So to draw the energy diagram, we have to know what are the bonds which are being broken in the reactants and what are the bonds which are being formed in the products and what are their energies. So for that we need the bond energy table which we have here. In the exam they will give you the bond energy table or the bond energies will be given in the question. So I have to show the bonds between the reactants and products to be able to understand what are the bonds which needs to be broken and what are the new bonds which forms during this reaction. The methane CH4 has this structure. It has four single bond between the carbon and hydrogen. It reacts with two oxygen molecule, which is O double bond O, and it gives us carbon dioxide, which is C double bond O, and two water molecules plus two water molecule, which has these structures and bonds. So what are the bonds which are being broken? So the bonds broken, we can see that we have four CH bond. So we have four CH bond that needs to be broken, and we have two O double bond O. We have two O double bond O. And on the products, the new bonds form. So I write bonds formed. You can see that we have two C double bond O. So I have two C double bond O. And for water molecule, each water molecule has two OH bond. One is here, one in another side. And because I have two water molecules, so totally I will have four OH bonds. So for breaking the bond, I need the energy. So I calculate the energy in. I have four CH bond. Here I have to find the CH. The CH is here, 413. And I have two O double bond O, which is here, 498. So 2 times 498. So the total energy in would be 2648 kilojoule per mole. And the energy out I have two C double bond O. C double bond O I don't have here in this table, so I have to find it in the textbook. It is 745 kilojoule per mole. So I have two of these bonds. As we can see here, we have 2 CO. So 2 times 745, and we have 4 OH bond, which is given here 464. 464. So the total energy out for this reaction would be 3346 kilojoule per mole. So now we can find the energy change for this reaction. The energy change or overall energy change equals energy in minus energy out. So energy that we need for breaking the bond minus the energy which releases by forming the bond. So it would be 2648 minus 3346 becomes negative 698 kilojoule per mole. This is the overall change in energy. So if I want to show this one on this energy level diagram, it would be like this. So at the beginning we have CH4 and O2, and we need 2648 kilojoule of energy for breaking those bonds. So if we give 2648 kilojoule energy per mole, so I write here kilojoule per mole, I can break the bonds. Bonds are broken. So we will have the atoms. Atoms then rearrange and the new bond forms, which by forming the new bonds, 3346 kilojoule of energy releases. So it releases more energy than the energy we need for breaking the bond, 3346, and we will reach to the products, which is CO2 and 2H2O. So we have answered part B, energy needed to break the bonds, 2648. Part C, energy given out by new bonds forming, 3346. The overall energy change is the difference between these two energy levels. So from here to here, and the overall energy change is negative, which shows that the reaction is exothermic. It releases 698 kilojoule energy per mole. On the next part, methane will not burn in air until a spark or flame is applied. Why not? If you look in these energy level diagram which we have drawn here, the reaction has two steps. In the first step, the bond between the reactants must be broken, and for that one, we need this amount of energy, and that spark actually provide us this amount of energy which we need for breaking the bond. If we don't have enough energy for breaking the bond, the reaction cannot happen. This amount of energy which we need to trigger the reaction is called activation energy. So this is activation energy. If the activation energy is provided, then the reaction can happen. Otherwise, the reaction cannot happen. Part C, when 1 mole of methane burns in oxygen, the energy change is negative 890 kilojoule. What does the minus sign tell you? So first, I have to mention that the value that is mentioned here is different from the value that we have got, because the bond energy which we use is different from the bond energy which the book has used for answering this question. So there are a little bit different bond energies in the different textbooks. So make sure that you use the bond energies which are given to you in the question or in the table. Part A, what does the minus sign tells you? The minus sign tell us that the reaction is exothermic and this amount of energy releases during the reaction. Part 2, which word describes a reaction with this type of energy change? We know that it's exothermic. And part D, how much energy is given out when 1 gram of methane burns? This part is cancelled and you don't need to answer this question. Now let's go to the last questions that we have here. Question number 5. It says the gas hydrazine N2H4 burns in oxygen like this. The reaction for the burning is shown here. Also the bonds are shown. Part A, count and list the bonds broken in this reaction. The bonds which are broken in this reaction are NH, and we have 4 of that one, and it's N single bond N, we have 1 of that, and O double bond O, we have 1 of that one as well. So I list them here at the bottom of the page. So bond broken, bonds broken. I have 4 NH bond. I have 1 nitrogen single bond nitrogen, and I have 1 oxygen double bond O. Part B, count and list the new bonds formed. The new bonds which are formed is nitrogen triple bond nitrogen and OH bond. For each water molecule we have 2 OH, we have 2 water molecules, so totally 4 OH bonds are being formed. I list the bonds which are formed here. Bonds formed. I have 1 nitrogen triple bond nitrogen, and I have 4 OH bonds. Part C, calculate the total energy required to break the bonds release when the new bonds form. The value for the bond energies are given here at the bottom of this question. So let's calculate the bond or the energies which we need for breaking the bond. So we have 4 nitrogen hydrogen, which is 391. So I have 4 391. I have 1 nitrogen single bond nitrogen. You should not confuse this one. This is the nitrogen single bond nitrogen. This one is nitrogen triple bond nitrogen. So I have 1 times 158, and also oxygen double bond O is 498, and I have 1 498. So the total energy which we need for breaking the bond is 2220 kilojoule per mole as it's given in the question. And the bonds which are formed, nitrogen triple bond nitrogen, we have 1 of this type of the bond. Its energy is 945, and 4 OH bond, its energy is 464. So the total energy which releases by forming the new bond is 2801 kilojoule per mole. Part D of this question says calculate the energy change in the reaction. So if we want to find the energy change, overall energy change equals energy in for breaking the bond minus energy out in the forming the bond. The energy in is 2220, Energy out is 2801. So it would be negative 581 kilojoule per mole of hydrazine. Part E, is the reaction exothermic or endothermic? This negative sign in the overall energy change tells you that the reaction is exothermic. Part F, where is the energy transferred from and to what? Okay, this energy which releases during this reaction was stored in the chemical bonds of the hydrazine. So the chemical potential energy transferred to thermal energy in the form of heat. Part G, and it also this energy transfers to the surrounding in the form of heat. Part G, comment on the suitability of the hydrazine as a fuel. So you can see here the amount of energy which releases for 1 mole of hydrazine is 581. So it's a lot of energy. But the problem that we have with the hydrazine is its availability. It's not available everywhere and it's not cheap fuel. It's expensive fuel. So that's why the hydrazine is not suitable fuel to use in everyday life. It didn't ask us in this question to draw the energy level diagram, but I want to draw the energy level diagram because it's very important question. So in energy level, I draw it here. We have the y-axis, which is energy, and the unit of that is kilojoule per mole. And we have the x-axis, which is the reaction progress. This is exothermic reaction. Suppose here is the energy level for the reactants, or reactants is hydrazine N2H4. Let's look at the reaction. We have hydrazine, it reacts with oxygen. So we have N2H4 plus O2. We have to give 2220 kilojoule per mole of energy to break the bonds. So if we give 2220 kilojoule per mole of the energy, bonds are broken. The atom rearranges and the new bonds form, and it releases 2801 kilojoule of energy. So it releases more energy than the energy needed for breaking the bond. So here is the energy level of the products, which is N2 and 2 water molecule, and the overall change in the reaction